Sections 1.9 to 1.10 are just kind of tying up some loose ends and sort of getting into some more of the theory of sets and how we can use them to say different things about numbers. So specifically, 1.9 is on sets that are number systems. So we've seen that a lot of times we want to think of the sets like n, the set of natural numbers, or z, the set of integers, or r, the set of real numbers. And not only are these sets, but they're also going to be, have some sort of built-in properties of those numbers. So what kind of properties are we talking about here, right? So we know that within these sets we can define something like addition. We can define something like multiplication. So I'm not thinking about set operations here. I'm thinking about operations on the elements of those sets. We can also define order. So we know what it means to compare saying two things are less than or equal to each other or strictly less than. We know what it means to say things are equal, right? So we have these extra properties of our sets. So when we're working in this sort of world where we're trying to build up things from the basics, we're going to take a certain set of basics and build off of them. So we're going to say that we know what numbers are. We know how to add numbers. We know how to subtract numbers. We know how to compare the order of numbers. But there's also some important properties of these sets that we need. So we're going to talk about a few of those examples here in this section. So the big one that we want to talk about, this big important property, is a property of n, and it's called the well-ordering principle. So what the well-ordering principle says is every non-empty subset of n has a smallest element. So you can think about that for a second. Think about why it's true. Remember, n is a set of natural numbers. So it's going to start with 1, 2, all the way up. I could take some sort of subset of that. And maybe I take the subset that only has 5, 6, 7. I could take the subset that has all of the multiples of 5. So it can be an infinite subset. I can take the subset that starts at 37 and then keeps going up by 1. Right? But all of these subsets of n, and any subset of n, always has some smallest element. That's what our well-ordering principle says. And it's not something we're going to prove. We're just going to sort of take it as fact, as a property of n itself. So I want you to think about sort of other sets and see if those have the same property. So is it true that every non-empty subset of Z has a smallest element? And what about R, or R plus, the positive ones? So see if you can think about what type of sets would or wouldn't satisfy this principle, that you're going to have that smallest element in all of your sets. To know, and then what can we actually do with this well-ordering principle? It actually is really strong, and we'll come back to it when we're talking about induction later in the course. But let's go ahead and actually do a specific example where we can really see this well-ordering principle in action. So given two integers, a and b, with b greater than 0, there's always a unique integers q and r, for which a can be written as qb plus r, and r is less than b. So this might seem a little strange, but it's probably something you're familiar with. So let's say I have a is equal to 25 and b is equal to 4. What I'm doing here, right, my q is my quotient, my r is my remainder. So I'm just writing 25 as some number times 4 plus a remainder. And the remainder has to be less than that b, so less than 4. So I know that 6 times 4 is 24. That's the closest I can get to 5. So I have that remainder of 1. So I have q is equal to 6 and r is equal to 1. And we can actually prove this using our well-ordering principle. So let's think about how that works. I'm going to consider the set A of all of the elements of the form little a minus x times b. So in our example, I'm going to start with my 25 minus 0 times b. Then I'll have 25 minus 1 times b, 25 minus 2 times b, 25 minus 3 times b, and so forth. 25 minus 6 times b. And I'm going to stop if this ever gets less than 0. So when I add one more multiple of 4 there, I have to stop because I only want the a minus xb's that are greater than or equal to 0. So I get all of these numbers. Oh, subtracting is hard. In my set, let me do this one. 25 minus 8 is 17. And I know that this set is going to be a subset of the natural numbers. So that has a least element by our well ordering principle. So let's call that least element the r. And then I know that r is equal to a minus xb for some x in z. So in particular, let's call that specific x, let's call that q. So I have r is equal to a minus qb. So then, if I rearrange things, I get that a is equal to qb plus r. That was the first thing I wanted to show. So I found integers r and q such that a was equal to qb plus r. And the other thing I wanted to show was that r was bigger than 0 and less than b. So let's think about how we do that. The least element in the set only contained elements that were greater than 0. So I know that r is greater than or equal to 0 since r is in the set. But it's also the least element in the set. So I know that if I increase my x by one more, so if I consider that x is the same as my q, the q plus 1 guy, that's not in the set because I'm considering the smallest thing in the set. So if I go one more, I'm no longer in the set. So if I consider a minus q plus 1 times b, that's not in the set, so that can't be greater than or equal to 0, so it's got to be less than 0, which means that a minus qb minus b is less than 0. Oops, I drew the wrong letter here. Oops. Let's fix that. So therefore, my a minus qb is less than b. But that a minus qb, that's just my r, so we really do get that r is less than b. So this is sort of a complicated explanation, right? But we are able to use this well ordering principle to sort of show these more complicated things. So I wanted you to see that. Okay, the last sort of property that we're going to talk about here is this Russell's paradox. So this comes from this idea where we're trying to build up a foundation of mathematics based on sets. And what you'll see, and we'll see in this video, is that there's some issues that we run into if we try to do that. So what I'd like you to do is watch this guest lecture. So it's just a YouTube video I found, and it talks really nicely about Russell's paradox and relates it to that Barber's paradox. So as you're doing that, I want you to listen closely to figure out what the Barber's paradox says, what Russell's paradox is, and sort of how those are related. And we'll talk about those in class.